Okay, here's my solution to number 85 on page 75 in Chapter 2 of the AP Chemistry text. The question concerns close packing in rubidium. So it tells us that rubidium has an atomic diameter of 4.95 angstroms. So the first question is, if you were to have a 1 centimeter cube, how many of these atoms could you, not a cube but a square, how many of these atoms could you pack on that square? All right. So basically all you have to do is you have to realize that it's just how many diameters you have divided into 1 centimeter. So we take 1 centimeter and we divide it by 4.95 angstroms. So this is part A. The conversion we have to do is just a little understanding that an angstrom is 4.95 times 10 to the negative 10th meters. Well, that means that really an angstrom is 4.95 times 10 to the negative 8th centimeters. So that's what I'm going to do here. I'm going to take 1 centimeter and divide it by 4.95 times 10 to the negative 8th centimeters. And that's going to, centimeters will cancel and you'll get how many atoms there are. Okay? So I have this, my calculator. Hopefully you can you see that display right there? Okay. So essentially I'm going to take 4.95 times 10 to the negative 8th. And what you have to do is invert it. You see that it's under 1, so I'm just going to invert it. And that's the answer. So that's how many will fit across. So that's 2, see scientific notation, that's 2.02 times 10 to the 7th. Across, of course, this is a square, so we're going to square it. I hit the squared button, and there's my answer, 4.08 times 10 to the 14th atoms. Realize, though, that significant figures, for some reason the back of the book rounds it to 2 significant figures. I forget, did this say 1 centimeter? Oh, that's the reason. It said 1.0 centimeters. So because this is 1.0 centimeters, that's 2 significant figures. So that's 4.1 times 10 to the 14th atoms. Okay, everybody sees how that's to solve 1. 1's pretty straightforward. The understanding in B part is this, that if you were to pack these, as close packing is what they're talking about, you can see that these fit into the dimples of the one they're above and below. Because of that, the way that they're closer together in this direction, in the up and down direction as I've drawn, but they're not any closer in this direction. So this number in the horizontal is going to be exactly the same number. It's going to be 2.02 times 10 to the 7th. The question is, what do we multiply by going down? They're obviously going to be closer together. Can you look at that for just a second and see if you can't figure that out? Okay, good. I hope you figured out that it was an equilateral triangle. Well, equilateral triangles are triangles of 60 degrees, and in this case, we're interested in the height of the triangle. So the height of the triangle, and again, this distance is 4.95 angstroms all the way across. The hypotenuse is 4.95 angstroms, and so how can we solve this part right here? Okay, the height. Well, that looks like an opposite over hypotenuse. So opposite hypotenuse, that's the sine of 60 degrees, is equal to x, in this case, by 4.95 angstroms. Okay? So that tells me that all I have to do then is to take the sine of 60 and multiply it by 4.95. And we get 4.287. So that means that the height here is 4.287 angstroms. So what is that? What does that tell you? Let's look back up at this picture right here. Oh, I've done all that off the page. Sorry about that. So take a look at what I did here. I've essentially solved that this is 4.287 angstroms. What does that information tell you about this? It tells us that the effective diameter of a rubidium atom in this direction is not 4.95 angstroms, but a little less, 4.287 angstroms. So I essentially have a rectangle now in which this value is 1 centimeter. This is 1 centimeter. I guess that's a square. But I'm going to be able to pack more into it because effectively this radius is now 4.287. This one, of course, we already talked about, didn't change. So we're going to multiply 2.02 from this previous step times 10 to the 7th times, let's see, we have to take this is 4.287 times 10 to the negative 8 under 1 because we're dividing that into a centimeter. And so that turns into be 4.287 8 inverted. So the number of atoms going down is going to be 2.33 times 10 to the 7th. So you can see I packed more in them. I multiply that by 2.02 times 10 to the 7th, and I get my new answer. My new answer is that the total number of atoms I get packed in now is 4.71 times 10 to the 14th atoms. There's the answer to B. The question then in the next part by what factor is this increased? Well, that means 4.71 divided by 4.1, which is equal to 1.148. 1.15 basically. So that's the answer to the next part. And then the next question is, would that be a more dense cube? And the answer is, of course, it would be denser because there are more rubidium atoms there per volume. Okay? So that's the solution that I had. It would be denser because there are more rubidium atoms per volume.